Did you know that the popular GraphSage algorithm, used in many graph neural networks, relies on a fundamental concept from graph theory called the neighborhood aggregation scheme, which can be represented using the mathematical framework of graph Laplacians and adjacency matrices? To understand this, let's start with some context. Graph neural networks, or GNNs, are a type of neural network designed to work directly with graph-structured data, such as social networks, molecular structures, or traffic patterns. At their core, GNNs rely on mathematical preliminaries from graph theory and linear algebra, which provide the necessary tools to process and analyze graph data. Now, let's dive into the technical deep dive. One of the key concepts in graph theory is the idea of a graph Laplacian, which is a matrix that represents the connectivity of a graph. The graph Laplacian is defined as the difference between the degree matrix and the adjacency matrix of a graph. The degree matrix is a diagonal matrix where the diagonal entries represent the degree of each node, while the adjacency matrix is a matrix where the entry at row I and column j is 1 if there is an edge between nodes I and j, and 0 otherwise. The graph Laplacian can be used to compute various quantities, such as the eigenvalues and eigenvectors of the graph, which can provide valuable insights into the structure of the graph. For example, the eigenvalues of the graph Laplacian can be used to determine the connectivity of the graph, while the eigenvectors can be used to determine the clustering structure of the graph. In Python, we can use the NetworkX library to compute the graph Laplacian of a graph, and then use the NumPy library to compute the eigenvalues and eigenvectors. Here's an example code snippet. Import networks as nx, import numpy as npg equals nx.graph, g.add_edges_ from 1, 2, 2, 3, 3, 1, l equals nx.Laplacian_matrix, g, eigenvalues, eigenvectors equals np.linealg.ig, l, print eigenvalues, print eigenvectors. This code creates a simple graph with 3 nodes and 3 edges, computes the graph Laplacian, and then computes the eigenvalues and eigenvectors of the graph Laplacian. The eigenvalues and eigenvectors can then be used to analyze the structure of the graph. Now, let's talk about linear algebra and its role in GNNs. Linear algebra provides the necessary tools to perform various operations on graphs, such as matrix multiplication, eigenvalue decomposition, and singular value decomposition. These operations are essential for many GNN algorithms, including GraphSage, which uses a neighborhood aggregation scheme to compute the node representations. The neighborhood aggregation scheme can be represented using the mathematical framework of graph Laplacians and adjacency matrices, which are both matrices that can be operated on using linear algebra. For example, the GraphSage algorithm uses a matrix multiplication operation to compute the node representations, which involves multiplying the adjacency matrix with the node feature matrix. This operation can be performed efficiently using linear algebra libraries such as NumPy or PyTorch. In real-world case studies, we can see the power of GNNs in action. For example, the company Pinterest uses GNNs to recommend images to users based on their past behavior and preferences. Pinterest's GNN algorithm uses a combination of graph theory and linear algebra to compute the node representations, which are then used to recommend images to users. The algorithm has been shown to outperform traditional recommendation algorithms, with a 20% increase in user engagement. Now, here's an actionable tip. If you're working with graph-structured data, try using the GraphSage algorithm to compute the node representations, and then use the resulting representations to perform downstream tasks such as classification or clustering. You can use libraries such as PyTorch Geometric or StellarGraph to implement the GraphSage algorithm, and then use the resulting representations to perform downstream tasks. Finally, if you want to learn more about the mathematical preliminaries of GNNs, be sure to subscribe to HumanOverAI, where we dive deep into the technical details of AI and machine learning.